In this problem, we are tasked to determine the weight of the heaviest cylinder which can be placed in the position shown without exceeding a stress of 50 megapascals in cable BC. Neglect the weight of bar AB given the cross-sectional area of cable BC is 100 square millimeters. We consider the free body diagrams of the cylinder and the rod. So for the cylinder, it will experience a force due to its own weight, let's call this W, and a force that is due to the contacting surfaces between the surface and the cylinder. That is the normal force, we call it N. And another force due to the interaction between the cylinder and the rod at this point here. We call this the reaction force between the rod and the cylinder. We call this force R. Now what we need here is the angle of R between the vertical. So by drawing a vertical line here that is parallel to the surface, and let's call this angle, let's say, theta. Therefore, this angle right here is also theta. And by constructing a line that is perpendicular, which is directly aligned to the reaction, we call it force R. And this is 90 degrees. Therefore, this angle right here is equal to 90 minus theta, which is this angle right here. And so for theta, we have a value of 6 meters, the opposite of this right triangle, and a hypotenuse of 10 meters. We can apply a trigonometric relationship using the sine function, that is sine theta equals to the opposite, that is 6 meters, divided by the hypotenuse, that has a length of 10 meters. Therefore, theta is equal to arc sine of 6 divided by 10. We get 36.37 degrees. And solving for this angle right here, that is 90 minus theta, we subtract theta by 90. We get 53.30 degrees. After that, we can solve for R in terms of the weight W, that is equal to mass times the gravitational acceleration, by taking summation force vertical equal to 0. So the weight going downwards, that is negative mass times the acceleration due to gravity, plus the component of the reaction going upwards, that is R, cosine of 53.13 degrees, all equal to 0. We get R equal to mg divided by cosine of 53.13 degrees. That serves as our first equation. And then once we have R, we can now consider the free body diagram of the rod that has a force equal to this magnitude of force R due to the interaction between the rod and the cylinder, and we have the tension, we call this T, due to the cable, and the reaction at the support A, that is a pin. So it exerted two forces along the horizontal and vertical direction. And R here has an angle of 53.13 degrees. And to solve for T without considering the forces at the pin support, we can take moment at point A, summation moment at point A equal to 0, considering counterclockwise to be positive. And then for the distance, this is 4 meters and this one is 6 meters. Therefore, knowing that this angle here is 53.13 and then this angle theta, which we solved earlier, that is equal to 36.87. We can solve for the vertical distance, that is the moment arm of T, equal to, that is 6 plus 4, 10 meters, cosine of 36.87 degrees. Then we can create our first equation, our equation for the moment at point A, that is T and it is positive since it would induce a counterclockwise moment times the moment arm distance of 10 cosine of 36.87 degrees. And then for the reaction R, there is a moment arm distance of 4 meters. It would induce a clockwise moment, so it's negative. So that's R times a moment arm distance of 4 meters equal to 0. And we know that R is equal to mass times the gravitational acceleration. So we can substitute R. That is equal to mass times the gravitational acceleration of 9.81 meters per second squared divided by cosine of 53.13 degrees times 4, all equal to 0. And then for T, we are given a stress of 50 megapascals, which should not be exceeded in a cross-sectional area of cable that is 100 square millimeters. We can solve for T by using the equation for stress that is equal to force T divided by the area. We get T that is just equal to stress times the area. So we have a stress of 50 megapascals or Newton per millimeter squared times the area of 100 square millimeters. Multiply this by the moment arm distance of 10 cosine of 36.87 degrees minus the mass times gravitational acceleration divided by cosine of 53.13 degrees times 4, all equal to 0. Now we have a single equation with one unknown. We can solve for n. So we have 50 times 100 times 10 cosine of 36.87 degrees minus m times the gravitational acceleration divided by cosine of 53.13 degrees times 4, which is the moment arm distance, equal to 0. Keep solving, we get our mass equal to no wait, this is equal to 611.62 or approximately equal to 612 kilograms, which is our final answer.